Let's take a look at another type of optimization problem, one dealing with area. That's usually very popular in college algebra as well. So this particular problem wants us to find the dimensions of the rectangular area that can be enclosed with 45 feet of fencing such that the area is as large as possible. And then they want us to find that area. So a lot of times what I'd like to consider for myself is I have to ask myself, what am I optimizing? So usually the words of the problem are going to help us out. So what are we trying to optimize? It's talking about area as large as possible. So it looks like we're going to, as large as possible, maximize the area. So a little note to myself, or to us, actually. We want to maximize the area. And then what are we finding the area of, though? And I kind of go back and I look at the shape. Very popular shape in mathematics. We're actually wanting to maximize the area of the rectangle. So I'm going to start by piecing items that I might know from my past to what we're dealing with in this section. So if I understand what it means to be an area of a rectangle, I do remember with how rectangles work, area is equal to length times width. So that's kind of going to be my key function that I'm working with throughout the problem. But as I'm going through this, in order for me to work with this, I need to have everything in terms of an independent variable and a dependent variable. And right now, what I have is I have area is dependent on two variables, length and width. So that could work if we have multivariable experience. But in this case, we will use our past experience to help us. I want to put area in terms of only length or only width. So goal at this moment, we want to write nicely. We want to, maybe instead of put, I should say write area in terms of one variable only. And we can take our pick. You either want it only length or only width. So in order for us to do this, we have to use the other pieces of information in the problem. And so when I'm kind of reading it, it's very short and it's tricky. Find the dimensions of the rectangular area. Well, that doesn't help us, other than we already have the area formula. That can be enclosed with 45 feet of fencing such that the area is large as possible. Okay, 45 feet of fencing. That's the other piece we have not used yet. Now that is not the area. When they talk about fencing, 45 feet of fencing, it means we are talking about what are we doing when we are going around the rectangle. So fencing is the measurement of the outside or the measurements of the sides of the rectangle. And there's a fancier word for that in mathematics when we talk about the sum of all the sides. And so we are going to use this fancier formula. We're going to use the idea of fencing to actually mean, I bet you guessed it already, perimeter. That might help us relate the two variables, length with width. These are notes to myself, but it's good while we're kind of watching anyways. Well, we all know how rectangles work. We do know that usually we call the longer side length and opposite sides are equal. So you see that I've labeled them on both sides. And usually we call the shorter side width. So I'll use a W. So if we talk about perimeter, we know that perimeter is the sum of all sides. We have a formula that we can come up with what do we have? When we add up all of the sides, we have 2L's plus 2W. So you might have already known that. Sometimes I like to develop it by drawing the shape and seeing what I come up with. But right now I have perimeter still being dependent on L and W. So I want to come up with one more thing to make sure. They actually gave me the perimeter already. So we actually have 45 equals 2L plus 2W. And now, my friends, we can write length in terms of width or width in terms of length. So you guys choose. I'll actually just solve it for one of the variables. So I'm going to solve for L, maybe because L stands for Laura as well. It's up to you. So if I solve it for L, that means I'd be subtracting 2W on both sides. And what I'm looking at, these aren't like terms, so I have 45 minus 2W. I have to write out horizontally equals 2L. And then if I'm going to solve for L, I need to divide everyone by 2. Now there's more than one way to do this, but sometimes I just divide everyone by 2. So I now have L equaling 45 minus 2W all over 2. So we do have length in terms of width. So what we've just done, and if you kind of take another math class beyond this, sometimes they talk about the idea of our primary equation versus a secondary equation. And primary equation is what we are trying to maximize. So this is the one we're actually going to be working with when we make our decisions and our calculations. But before we can deal with the primary equation, we have to deal with a secondary equation. And that's where we're getting our perimeter, all different forms. And now we kind of reach back in our past math lives and we kind of say, well, if we do have two equations and two variables, we can use a method of substitution to help us rewrite everything in terms of one variable. So again, we care about the maximizing the area. So we want to plug in whatever we wrote L in terms of. So in our case, the area now is length times width. The length's a little more complicated. Don't let this throw you off. We'll deal with it in a second. So 45 minus 2W over 2. And that's still multiplied by a W. So now we have area in terms of one variable only. It's the width. Check. We got it. Now, it's up to you if you want to further investigate what is going on here. What I'm noticing is that it doesn't look like any sort of quadratic function that I'm familiar with, but that's because we have two factors going on. You could play around a little bit if you're interested in saying, well, I do know that I am dividing by a monomial, so I technically have 45 over 2 minus 2W over 2, still multiplied by W. So 45 over 2 is just a number. 2W over 2 is just minus W, still multiplied by W. And now if we were to distribute that W, you'd actually get 45 over 2 times W minus W squared, and that is the area. So it's another version, but now you kind of notice squared term, linear term. It seems to be like a quadratic function as well. So it kind of verifies it for us. In fact, if you notice that the squared term is negative, you already kind of know what's happening with your graph before you even graph it. So now we are feeling pretty good about what we're trying to maximize, but the idea is we have to actually find the answer to the question. and they wanted to figure out the dimensions of the area that can be enclosed with 45 feet of fencing, such as the area as large as possible. So basically, if we have to maximize this, maximizing the area, it's another way to say find the vertex. And so it's totally up to you how you want to find it. The directions did not specify what technique to find. Some of you may like the formula method, and you probably would use this version so that you actually know who the A and the B are. And if you decided that you didn't want to go through the math and you wanted to use this original version, you could also do that too with your TI. So I'm going to use the TI just to kind of show you, and feel free to verify on your own. But if I were to now plug everything in, I'm going to have to probably switch back and forth, but I'll call up the TI one more time. So we have our old problem from our past. And you know, sometimes while you're working on the optimization problems, it doesn't hurt to keep your old windows. Zooming back to standard would just make you have to zoom back out again. So I'm going to go in and I'm going to type whatever version that I had. So I need to check one more time to remember what I had. 45 minus 2W over 2. Okay. Go back so you guys can see. And there's a specific way, you know, we got to be careful when we're typing in fractions on the calculator. So I kind of want to make sure if I have this, I'm going to have, maybe it's even better if you have this. You could use the fraction key, but I'll go with it. What I'm looking at is I have to be extremely careful because I don't want the extra W to end up in the wrong spot. So 45 minus 2x divided by 2. What I did is I enclosed all of that in parentheses so that I know I'm still multiplying by an x. Sometimes it is worth it to actually do the math and so you have a nice quicker quadratic function to type in. Sometimes your TI takes a little longer thinking about it as well. So it's kind of, there's pros and cons to all of this. Press enter, and I'm going to graph, and I have my old window. You can kind of see my old window is a bit too high, but I do see some sort of parabola happening. So what I might do, it's up to you, but I might kind of notice that maybe my Y max is a bit huge. So maybe 3,000, 30,000, I don't know, let's go with 5,000 first. Sometimes I make guesses and sometimes they work and sometimes they don't. So we'll see, yeah, we're still a little too high. Maybe I'm a little too low as well. So yeah, my Y min. We all know that we can't have a negative area. So why don't we say 0? Now we're kind of seeing, okay, well, we're still a little too high on there. So again, I'm playing with my Y mins and Y maxes. I don't try to play with everything at once until I'm feeling pretty good and confident. I think my Y max is a bit too high. Maybe I cut it into 1,000. And remember, it's all trial and error, but you can make educated guesses. Let's try it from there. I mean, so we do see a vertex, and that's good. But if you're like me and you want something prettier and a little more centered, you might consider maybe making the Y max. Maybe we'll go down to 500. See what happens. And maybe I'll take it even smaller. Maybe I'll say it's 100. And I noticed that my X max is pretty huge. So, how about I make it 50? It's always a battle, right? I really want to see my vertex. I think I went too low on the Y max. So let's just go back to where we started. So there's nothing wrong. It happens all the time. We're not always right on the first case. All right, I guess I'll live with it, but feel free. I might say 250 if you guys really want to. Okay, I'll do that since you asked. There we go. I feel pretty confident about that parabola. And any of the versions, as long as you see the vertex, you could have calculated it already. So I just wanted to take you through that. You know, it's not always the first shot that you see the pretty picture. So just be patient. So let's calculate what's our favorite buttons. Second, trace. And we are calculating a maximum. And so we're going to use the arrow key. Get a little to the left of where we think our vertex is. Sometimes I exaggerate. A little to the right. And we have our maximum. So we have 11.25 and 126.5625. And it looks like it's a never ending, it's a terminating decimal. So I might just keep the entire number for myself for accuracy. So let's see. Let's see if this works for us. So we will go back. And we do have a quick sketch if that's something that you're interested in. Kind of a quick sketch if you'd like to. Something on the line of this. And again, there's that vertex. So we figured out that the vertex was 11.25. And sometimes my memory goes, so I have to reference back. I'll go back and check. It was 126.5625. Okay. Go back. So that's all nice mathematically that, hey, we found the vertex. But the very last thing is to check, because we have a problem that talks about some sort of real life context. We want to make sure that we're answering it in plain English instead of math speak. So I want to make sure if I'm trying to answer the question, it's asking me to find the dimensions. Okay, so first off, the dimensions that maximize the area. Now remember that the way our graph is graphed, we have area as a function of width. So technically, instead of a y-axis, we have an a-axis. Instead of an x-axis, we have a w-axis. So it's kind of nice to kind of note what part of the vertex stands for what type of measurement. So when we speak about width, and if we're kind of really looking at this, it looks like the width is going to be 11.25, and we want to find out what's actually the what was the right word? Excuse me, the units on this. So 11.25. So we're going to talk about dimensions. So width, we know for sure is 11.25, but we got to go back and say, what did we speak about? Well, the only type of reference to dimensions was feet, so there it is. And whenever they talk about dimensions, notice the S, plural, they want us to find the length. So in order for us to find the length, we kind of have to use how they're related. So I'm going to go back to my perimeter formula and kind of say, well, if W equals 11.25, if I plug it back into my, my formula solved for length, or my equation, I have 45 minus 2 times 11.25 all over 2. That's going to give me my length. Quick calculator. 45 minus 11.25 times 2. That's 22.5 all over 2. I'm kind of saying, okay. 45 minus 22.5, 22.5 over 2. Really, we want to see this, divide by 2. And look at that. The length is 11.25 feet as well. So you're probably guessing, wait a second, if the width and length are the same, don't we in fact have a square? And the answer is yes. So I believe having a square, which is a special type of rectangle, would be the correct dimensions to maximize the area. So double check one more time. Did we find those dimensions? Check. And the last thing, did we find that area? One last thing. Finding the area. And actually, we actually already had the area because it is the vertex. It is the highest A value or Y value if you're talking about this. So the area is actually 126.5625. And we are in feet, but remember area is feet times feet, so we have square feet. Or if you'd like, mathematically, you can kind of use an exponent, but you don't really see that too often, I guess, in the real world. And you can verify if you were really trying to figure out what is area. Area is length times width. If you say 11.25 times 11.25, do we in fact get 126.5625? Yes, we do. You probably guessed that already. So just kind of remember when you're dealing with these problems, a lot of times, anytime you are dealing with a quadratic function, finding the vertex is usually a really important part of the problem, even if they don't straightforward tell you. But the other important part of the problem, besides finding the vertex, is being able to interpret the two values that you are finding. So just be careful, read the problem. When you think you're done, read it one more time and always double check, have I answered anything and everything that the problem wants? I'll see you next section.